So, in this session, Amit will present SQL Server Memory internals and troubleshooting. And take it away, Amit.
All right. Good morning, good afternoon, good evening, depending on where you have joined from. Welcome to another conference by Groupby. It's difficult to say that by Groupby. So thanks, Daniel, Misha, Blythe, and all of you. This is a wonderful concept, and thanks for having me as a speaker, and thanks for the opportunity to deliver this session. So today's session, my topic is about SQL Server Memory internals and troubleshooting. My name is Amit Bansal, and I have been working with SQL Server since '99 formally, and have done a lot of work around SQL Server performance, troubleshooting, query tuning, large-scale deployments across different versions of SQL Server. I also have a small YouTube channel. YouTube is never small, but this channel is small, which is YouTube/SQL Maestros, where I keep recording a lot of SQL Server videos, and whenever something is good enough, I post it up there. Because you are today's attendees in this session, you can also stay connected with me on this URL, which is right in front of you, connect with AB, bit.ly link. You can use that, and that's an exclusive list for all attendees who join my session, either in person or online. And I don't publicize this URL elsewhere, so it's always only for the attendees. Quickly about my work, I am also a Microsoft Certified Master of SQL Server, also an MVP. This is my 12th year running, and Microsoft has also awarded me as a regional director. SQLmaestros.com/Amit-Bansal is where you can go and learn more about me and my work. I am associated with SQL Maestros for a couple of years now, and performance tuning video course is one of the flagship things under SQL Maestros. There are learning kits, there are hands-on labs, and of course, master classes. On a community front, of course, whenever I get an opportunity, I speak at global conferences. And I'm very fortunate that I've been selected as speakers at almost all conferences like Ignite, TechEd, PAS, DPS, SQL Bits. And I run a small community right here in India, which is Data Platform Geeks, and we also organize a local conference for the Asian community here, which is Data Platform Summit, and those are the URLs in front of you there. Now, before I begin today's session, here is a quick warning for everyone. So SQL Server Memory is convoluted, and it's of course confusing, complicated, and there's just too many things about it. There are so many pieces that are connected to understanding SQL Server Memory. And let me tell you, before even I started diving deep into SQL Server Memory, I spent quite a bit of time learning about Windows memory in the first place. So if you think that today, after attending this 1-hour webinar, you would really know everything about SQL Server Memory, you will be up for some disappointment because you got to really spend a lot of time learning about reading about, rather, I would say, about Windows memory and then SQL Server Memory, about the hardware architectures, about NUMA, and a lot more. So in this 1 hour, I'm really going to give you good practical information that you can kind of take away and start using it in your production environment. That probably would be the real value of your time joining today's webinar. So what are we not going to talk about? Let's see that first. So I'm not going to give you a list of all the performance counters that you should be watching, whether their numbers are good, bad, or ugly. I'm not going to give you a list of all the DMVs that you should be tracking down with all those beautiful numbers in those columns, and then you know what those numbers are, and in many cases you would not know what those numbers are. We are not going to talk about all the possible memory pressure scenarios. And of course, we do not have enough time to cover all the architectural stuff. So this is not what we're going to do. What are we going to do? We are going to focus on specific things. And first, I will begin by understanding what NUMA is. SQL Server is NUMA compliant. So it is important for you to know what NUMA means and how does SQL Server deal with NUMA. Then we will cover SQL Server memory architecture very briefly and how it talks to Windows. And this coverage about SQL Server memory architecture is only going to be limited to you kind of really benefiting from that knowledge. Rather than trying to satisfy your intellectual curiosity, I go keep deep and deep and deep and talk about a lot of theoretical stuff, which you may not consume practically. I'm not going to do that. We will then move on into understanding how you can track memory usage inside SQL Server component-wise. Then we'll look at a few memory pressure examples, and then remaining part of the webinar, I'm going to focus on demos. So this is going to be a fast-paced webinar, so please try to keep up with me. Let's first talk about NUMA. So what you see in front of you is a symmetric multiprocessing system, and you can see a diagram where there are 4 CPUs and they're talking to a single memory controller. And whenever CPUs need memory, they talk to this memory controller, and the memory controller will take memory from the physical RAM that is available on the hardware box. Now, what happens is everything is good when you have like 4 CPUs or 8 CPUs, but the moment you scale up and you add more CPUs, 16, 32, and you way to 96 or 192 and whatnot, and highly scalable hardware, modern hardware, then having just one memory controller is not enough, because there is going to be contention. And this is something that was kind of detected pretty early in the hardware cycle. And you have a lot of CPUs, you have a huge amount of memory, yet everything is so slow. Because so many CPUs are talking to the single memory controller, there is contention at that memory controller. And there comes a hardware design, which we call as non-uniform memory access or non-uniform memory architecture. Choose whichever abbreviation you like. And then you can see this diagram in front of you where the CPUs and the memory is partitioned by NUMA nodes. So this is what we call as physical partitioning. This is physical bifurcation at the hardware level. And now you can see that your hardware has more than one NUMA nodes. This is what we also call as a multi-node system. So you have node 0 all the way to node 1, 2, 3, depending on how big your hardware is. What's important to note now that each node has its own set of CPUs and its own memory controller. That's how this partitioning is done. And CPUs can talk to its memory controller, and take memory from that node, which is called as local memory access. And in case, so so the CPUs in every node are talking to their own memory controller. And whenever they want to, let's say the memory is not enough really in that particular node, and there is a need to ask for more memory, they can do a cross NUMA node memory allocation, which is also called as foreign memory access. So let's take a typical example. In this case, you have 2 nodes, node 0 and node 1, and let's say you had 64 GB on your box. So your node 0 will have 32 GB and node 1 will have 32 GB. And this box had 16 cores or 16 CPUs, then your first node, node 0, will have 8 CPUs, and your second node will have 8 CPUs. So this is physical bifurcation of 2 nodes. What is the purpose of NUMA? Well, the purpose of NUMA here is faster access to memory. It just really solves that one problem, faster access to memory. Now, the architectural concepts of NUMA is, of course, there are many, many more things about balancing memory access in these nodes and imbalances, and how the physical interconnect works, and different design patterns with NUMA. But as I said, we're just understanding this conceptually. You can, of course, read more online if you want to understand this in more details. And why were we talking about NUMA right in the first place? Just to set the basics and the foundation here, that SQL Server is NUMA compliant. SQL Server is NUMA aware. And we'll talk about that in upcoming slides. Now, the time has come to talk about SQL Server memory myths. There are a couple of misconceptions about SQL Server, so let's get them cleared off first, so that all of you, and of course me, we are all on the same page. First, SQL Server memory management is pretty much automatic memory management. It's designed that way. You have very few knobs and switches to control SQL Server memory. Things like you have min memory setting, you have max memory setting, you might have some settings in resource governor, you have locked pages in memory, you have a configuration that many of you might have never used, which is like minimum amount of memory per query and things like that. Well, that's really what you have from a memory configuration perspective. And why it's automatic memory management? Well, the saying is that Microsoft SQL team, they want you to focus on more important things rather than hacking your brain with managing SQL Server memory in a fine-grained manner. However, the knobs and switches that are given to you are pretty good enough for you to kind of exercise some control over how the memory thing works. lot of questions come in forum, and let me try to kind of answer it from a Q&A perspective. So common question. I have 64 GB on my box and SQL Server is eating up all the memory. And why is that so? Why doesn't it release memory back to Windows? So SQL Server is designed that way. You give all the memory to it, it will take all of it. You have 64 GB, you add another 64 GB to your box, SQL Server will happily take all the memory, provided you have not set min, max, etc. Typical vanilla installation, SQL Server will take all the memory that you give to it. Well, it's a no-brainer. Any database software, of course, SQL Server, they would like to keep everything in cache because memory is much faster than disk. And let's say you have large databases that are running into gigabytes and terabytes. So, of course, buffer pool being one of the biggest memory consumers inside SQL Server would like to cache those data pages in memory so that the retrieval is much faster. So there's no point complaining about that SQL Server is eating up all my memory. I will show you techniques how you can find out where is that memory being used inside. But the answer is SQL Server is designed that way. So when does SQL Server return memory back to Windows? Well, when there is an external memory condition, let's say you're running some applications on your box other than SQL Server, it could be IaaS, it could be analysis services, or you're running an integration services SSIS package that is kind of memory heavy, and there is an external memory condition, SQL Server is, of course, going to ping you back, and there is a resource monitor thread that's running inside SQL Server, and a low memory notification is going to go, and you can track that information in OS ring buffers, DMV, that there is a low memory notification coming in. When that happens, SQL Server is going to release memory back to Windows in a phased manner. That's the basic idea about automatic memory management and SQL Server releasing memory back. Now, question is, how much memory can SQL Server consume, and up to what point will it return the memory back? Well, these things are decided by the configuration that you do with min and max. So let's say you have 64 GB RAM on your box, and you have set max to, let's say, 60 GB, which is a soft limit. So you're telling SQL Server that go all the way up to 60 GB, but not beyond 60 GB. So, I mean, practically speaking, you could see the SQL Server engine actually consuming 61 GB also, because as I said, it's a soft limit, or maybe even slightly lesser than that. So it's always a good practice to set the max value. You should never leave max to whatever the default it is. Why? Because in such cases, SQL Server can actually put Windows under pressure by trying to squeeze every byte out of the Windows memory. How much memory should you leave for Windows? Let's say you have 64 GB box, you could leave about 2 to 3 GB for the Windows operating system. You could leave about 1 to 2 GB for the thread stack. You could maybe leave another GB for some utilities that are running, backup utilities or anything for that matter. And in totality, you could just leave about 4 to 5 GB, and rest you could set for SQL Server. So, on a 64 GB box, that number could be 59 or 58 or even 60 for that matter. In this scenario, of course, I'm not assuming that you're running IaaS or any other pretty memory-intensive applications, because going by the best practice, if it's a heavy production, high transactional system, or a big OLAP server, SQL Server should be the only application running on the box, just going by the best practice. What about minimum? Now, so there's a misconception about the min setting, and some people think that min means that if you set a value for min and SQL Server boots up, SQL Server will immediately notch up that much memory, whatever you have set for min. That's actually not correct. Min value here would mean that SQL Server will take whatever it needs, and when it begins, like when it starts up, it will probably take a few hundreds of MBs, and as the requirement grows, it will keep asking more and more memory from Windows, and it will keep piling up. And the moment it reaches that min threshold, let's say you have set min to 32 GB, the moment it reaches 32 GB of memory consumption, it will never go below it. That's what min here really means. So that's the kind of some clarification around min and max. A lot of people tell me that, okay, it really makes sense to put some value for max. Okay, so I think I can see some questions coming in. Okay. Yeah, it came in chat window, no problem. So I'll take all those questions at the end of the session. Thanks, all of you. So when you talk about the min and max. So audiences do ask me that it makes sense to actually set value for max, but what about min? Is it really important? I would say, yeah, you should go for it. You should not leave min to, let's say, 0 or whatever, because you also want predictable performance from SQL Server. For whatever reason, you don't want Windows or any other rogue application or anything trying to kind of pressurize SQL Server to release all of its memory back. So that's what was with min and max. There's another clarification about max that I want to talk about. You know, in versions prior to SQL Server 2012, max actually meant the maximum amount of memory for SQL Server buffer pool. Now, starting from 2012, that has changed. Buffer pool as a memory consumer inside SQL Server in early days, in days prior to 2012, used to be a memory consumer as well as allocator. So whenever SQL Server had to do, so there were two types of allocations inside SQL Server. Sorry, I'm deviating a bit, but just trying to kind of give you some background. There were two types of allocations inside SQL Server: single page allocator and multi-page allocator. Single page allocator means allocations in 8 KB chunks, and multi-page allocations meant any allocation which is greater than 8K. So multi-page allocations used to come from VAS, which is virtual address space, and single-page allocations used to come from buffer pool. So buffer pool used to be a memory allocator as well as memory consumer, and max actually meant the maximum memory for the buffer pool. But starting from 2012 onwards, of course, thanks to SQL team and Microsoft, they simplified it. Max actually means max. And there's a caveat there, almost, which means that, of course, there are a few things again, but max would really mean max now. Max for the engine, and that's max for the SQL Server. And buffer pool now is only a memory consumer. It is no more an allocator. The concept of single page allocation and multi-page allocation is also deprecated. And you right now have only one allocator, which is called as any page allocator of any size. Also, going by this information of what was changed from 2012 onwards was deprecation of 32-bit support and AWE mapped memory. AWE stood for addressing Windows extension, and then Intel specific switch, physical address extension, etc., and /3GB, and as I say, blah, 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 all of that. All of that was deprecated because many of you might know all of them were workaround for SQL Server process to access memory beyond 4 GB, because there was this restriction of 32-bit pointer can only point up to 4 GB. So if your box has more than 4 GB, how can you really consume memory more than 4 GB? So all of them were workarounds. All of them came with their own pitfalls, their advantages and disadvantages. And of course, it was dirty work all around. So good, it is gone. Now let's talk about the internal and external memory pressure. So there are, of course, when we talk about memory consumption, and let's say SQL Server is consuming a lot of memory, what do we really mean by internal and external memory pressure, or how do you really define memory pressure? Internal memory pressure is caused by conditions inside SQL Server, and which means there could be buffer pool, right? Really doing very high churning of memory, plan cache, a lot of ad hoc queries are coming in, and there isn't enough space in the plan cache to really do very high churning of the plan cache, which is get in new plans, make space, and kick out old plans, those kind of things. So this is what we call as internal memory pressure, that is conditions caused by components inside SQL Server. And external memory pressure would mean that conditions created externally, which is outside the process of SQL Server, which could be Windows, and let's say someone just kind of ran a full scan with an antivirus package or anything as silly as that on the server. So that is external memory condition. And of course, there are many ways to track that and what's going on inside. So I will talk about a bit more about memory pressures and conditions later in the session. Memory used by a single query, by a single session, I'll leave that for the moment, just for the sake of brevity and for the sake of time. Now, let's move forward and welcome to the dungeon. So now I'm going to talk about SQL Server memory architecture. And now if you're wondering, what was I doing all this while? Well, I was talking about SQL Server memory, trying to demystify a few misconceptions, but I use this parody as a dungeon because dungeon is dark and there's unknown area and it's pretty scary out there. And yes, SQL Server memory is scary. So right now what you have is a slide in front of you that gives you a very pictorial illustration of what SQL Server memory may look like. And let me see if my zoom in works, and then I'll try to draw a few things. Okay, so on the left hand side, the first thing that you um, sorry, okay, first thing that you see is the physical RAM. Can I just use the highlighter here, and I think that'll make things a little more easy. Okay, and I can just change the color to red maybe. Yeah, okay. So on the left hand side, you have the physical RAM here, as you can see. And that blue bar denotes the physical RAM. Let's say your box has 32 GB RAM, and all these smaller boxes here denote the physical addresses. Then you have the NUMA nodes, and now we come to NUMA. So we talked about NUMA in the first slide itself. So let's say this physical RAM, let's say 32 GB, is bifurcated, partitioned, physically partitioned as NUMA node. So you have NUMA node 0, you have 1, 2, and 3. There are 4 NUMA nodes. The physical RAM that you have on the box, from inside SQL Server, you can track the OS process memory and OSS memory. These are two very important DMVs, and I'll tell you, I use them almost daily to kind of understand two things. One is, what is the memory consumption and how it's going on for the SQL Server process, which is OS process memory, and at the system level, how does SQL Server really see Windows memory? That is answered by this DMV. So two very important DMVs. Just to get a very high level overview of my memory numbers. We will work with them when the demo comes. Then comes your NUMA nodes. Now, we're still not touching SQL Server. We are talking about the physical RAM, and then you have the NUMA. So the physical memory is partitioned, physically bifurcated by these NUMA nodes. You can actually track all these nodes inside SQL Server using a DMV called DIM OS nodes. And you can see all of them are under this category of OS, which actually stands for SQL operating system. And that's why you have DIM _ OS _ nodes. Now comes the memory nodes of SQL Server. And this is the point that I was trying to make when I was actually talking about SQL Server being NUMA aware or SQL Server being NUMA compliant. For each node, for each NUMA node on Windows or on the hardware, SQL Server will create one memory node for itself. So if you have 4 NUMA nodes, you will see 4 memory nodes inside SQL Server, and there is a one-to-one mapping. And that's how physically inside SQL Server memory is partitioned and bifurcated. Now, why is it important for you to know? Many of you are working as developers, DBAs, and architects, and you know inside SQL Server, there are a lot of these background threads like checkpoints, lazy writers, resource monitor. Depending on how many nodes you will have one lazy writer for each memory node. You will have one checkpoint for each memory node. You will have one resource monitor for each memory node. So if I have 4, I will have 4 threads for each of them. That's how SQL Server will treat each node exclusively. And then we will see how allocations happen. So allocations will happen via these memory nodes. Well, now what happens inside SQL Server when components need memory? So now I am saying SQL Server components. What are these SQL Server components that need memory? Well, one classic example is buffer pool. As I said earlier, buffer pool is a memory consumer. So it's a component inside SQL Server engine that needs memory. Then there is plan cache, and then let's say there are optimizers. There is a query compilation engine, and then let's say there is the optimizer reserving memory for optimization phases. Then let's say when you send a select query to SQL Server, a parse tree, a query tree is created inside it. There is memory needed for that. Now, if you see, in all, there are just so many components inside SQL Server that need memory. When they need memory, they have to talk to these memory nodes, or rather I will put it this way, the access to memory is done via these memory nodes. Memory nodes will actually allocate or consume memory, or in other words, they will call these Win32 APIs called base allocators or structured allocators. Now, when you talk about these base allocators and structured allocators, these are Win32 APIs. So under base allocators, let's say you can see a virtual alloc X, and then virtual alloc extension NUMA, or the AWE allocations via physical pages and physical pages NUMA. These are base allocators. Now, base allocators actually provide a raw interface, and they allow you to block memory in large chunks. So when you are actually blocking memory in large chunks, the good thing is you might have more control over the memory, but the bad thing is memory management becomes inefficient. And that's why you have another type of allocation, which we call as the structured allocators. And I'm sure even if you have not heard about Win32 APIs like these ones under base allocators, I'm sure some of you might have worked with C++ and you will probably remember about heap alloc and malloc and new. These were structured allocators given to consumers and programmers to allocate memory in small chunks. So this is for small and simple allocations, but then these are small chunks, so you don't really have too much fine-grained control over it. But remember, structured allocator, if you're using these APIs, they will definitely anyway call the base allocators and in turn talk to the Windows physical memory to allocate memory. So if you see SQL Server Memory, but in a way I can say that SQL Server Memory is a 3-layered architecture. Not talking about the RAM and the NUMA nodes, but starting from the memory nodes here, this is my layer 1, and then I have memory clerks on top of my memory nodes, and then I have memory object on top of clerks. Let's try to demystify and see what's the relationship between clerks and nodes and objects. Well, I was talking about memory nodes. Now this slide is getting a bit messy, so let me kind of clear off the screen. And where is that option to off screen? Okay, there you go. Oops. So we'll just take the marker once again. So it came back again. Okay, there you go. Now let's talk about the memory node. So you can actually track all memory nodes using sysdmos memory nodes. And when you do a simple select star from this DMV memory node, you would, on your laptop, maybe you would just see node 0, which is like a non-NUMA system, because having no NUMA would just mean the one node, the default node with node 0, and you would see another one for DAC, which will be node 64. So I briefly just talked about this memory nodes. Now let's talk about memory clerks. So what are clerks? Clerks give you one answer. How can I track memory usage inside SQL Server component-wise? So if you want to track component-wise memory usage, you would go to clerk. And now the moment you look at this clerk, by this diagrammatic illustration, what I'm trying to explain is clerks have all different sizes, and you can see buffer pool is also a clerk. Now that's an important piece of information. Everything that needs memory inside SQL Server probably has a clerk. So buffer pool is a clerk. The caches, all the caches are clerk. So you can see there are different types of clerks here. You have a general clerk, you have a user store, you have an object store clerk, and then another classification of clerks are the cache stores. So if you see the cache stores here, I'm just trying to kind of put down all the cache stores. So you can see cache store objcp, which is for your object plans like store procedures, triggers, and user-defined functions. And then you have cache stores for your ad hoc plans. Bound trees, this is the one I was talking about, the query trees. So there is a cache store called PHDR, and then of course extended store proc. So caches inside SQL Server are also nothing but clerks. They are called caches because that's another classification. And there are objects coming into the cache stores and moving out, and there is a flushing algorithm there, and which we actually inside SQL Server call as the clock system, which is like an LRU algorithm keeping track of the least recently used object, how many times a plan cache has been used, when was the last time the plan actually came in, etc. And this is very high churning. So imagine a heavy transactional system where there are hundreds of ad hoc queries coming in with lots of different parameter values. So you can imagine what kind of churning will be required. So SQL Server Engine puts this brokering system and the clock system in place to make sure that these cache stores are very efficient. Okay, now let's go back to the clerk. So as I said, clerk will help you track memory usage inside SQL Server component-wise. When clerks need memory, they have something what we call as the clerk interfaces, and they are going to call those clerk interfaces, and of course in turn they will basically be calling the structured allocators or base allocators via the memory nodes. So this is how, from a let's say simplified understanding, I could say that clerks are talking to memory nodes as they need memory, and memory nodes in turn are calling these APIs as and when they need memory. Now, at the bottommost layer, you have something called as memory objects, and memory objects are the granular level, and you can see hundreds and thousands of memory objects as and when memory is consumed. It's not like the clerk has taken a few hundred or a few GBs of memory. They're all broken down into what we call as memory objects. So memory objects will allow, are basically the components that will, memory objects are the pieces of object that will actually uh, consume memory in a very, very structured way. And for a given clerk, you might see hundreds of memory objects. So theoretically speaking, for a given clerk, I can actually sum up all the memory objects, and the total sum should be actually equal, to the memory consumed by the clerk. And let's sum up all the memory consumed by the clerk. That should be equal to, theoretically, should be equal to the amount of memory consumed by SQL Server exe. You can track all the clerks in this DMV, sysdm OS memory clerks, and you can track all the memory objects in this DMV OS memory objects. From a SQL Server memory consumption and troubleshooting perspective, clerks and objects play a very, very critical role, and the demo will prove that. Final few thoughts about SQL Server memory architecture. SQL Server memory has three models. Conventional model, you can see on the top right corner, conventional model, logged model, and large model. If you do a plain vanilla installation of SQL Server, that is conventional without any configuration changes. That's conventional model. If you turn on locked pages in memory, which means you're telling SQL Server that on Windows that, you know, the amount of the physical RAM that the engine is consuming should be in the memory. It should remain in the physical RAM, should not be paged down to disk. So there should be no soft page fault or a hard page fault, and which is a good practice for SQL Server because you want that memory to remain in memory. That's the locked memory model. And I assume many of you are already running your SQL Server environments in locked memory model. There is a kind of an uncommon memory model also called as large, not very commonly used. Large memory model will turn on large pages. So there are certain prerequisites, like you need to be on enterprise edition, you need to have more than 8 GB of RAM, and lock pages should be turned on. So if these three options are true, if these three conditions are met, you're telling SQL Server to support large memory model. And if you want to force large memory model, you can turn on the trace flag 834, and that will enable and force large memory model use. Well, then what is large memory model? Well, large memory model will allow SQL Server to reserve all the available physical memory of Windows up front when it starts up. Think about it. So if your SQL has, your box has 64 GB and you've set max to 60 GB and you have turned on large memory model, the moment you start SQL Server, it will reserve all the 60 GB upfront. Why? Because large memory model will allow you to access memory in a contiguous manner. So you want large chunks of memory in contiguous fashion, and that's when you will use the large memory model. It will also turn on the large page options. On 32-bit system, the memory page size is, let's say, 4K, but on 64-bit systems, it's from like 2 MB to 16 MB. So turning on the large memory option there. Now, there is this big brother resource monitor that is always running there, trying to see what's going on with SQL Server memory and, you know, overall performance. Is the system doing good or bad? And whenever SQL is under memory pressure, internal or external, it sends output to this DMV, DIM OS ring buffer. And you should, from books online or MSDIM, you can get some queries to actually parse the XML data out of DIM OS ring buffer to see how the system is doing good. Well, friends, that's pretty much on from this slide. So let's move now, and let's look at everything that we talked about in demos so that we can enforce all the concepts that we have learned. So this was a brief architectural thing. So let me jump to the VMB, and if Daniel can confirm me that he's able to see the VM, it should be good.
Absolutely.
Okay, perfect. Thank you, Daniel. So first things first, I have just started SQL Server now, and if I look at DIM OS process memory and I click on execute there, you can see SQL Server is currently consuming only 362 MB of memory. Now, there's always this question about what the best way to track SQL Server memory usage? Is it the DMVs? Is it the task manager? Is it the perf counter? Well, task manager is obviously out of question. But yeah, you can always kind of peep into it. But I would recommend that go for Windows perf counters and the DMVs. In perf counters, there's a specific counter called total server memory. So that's a good counter which will give you kind of good accurate information about SQL Server exe consumption. Remember, that is about the SQL Server exe engine consumption. This is about the overall process. So there is some amount of memory which goes outside the exe, out of process, and that will actually show up here. So you can see, and you can now see that large page allocation is 0 and log page allocation is all 0 because I'm actually running in conventional model. And as I said before, I am not really going to go and talk about every number out there. That would really take a whole day. And if you take all the DMVs, it might take a whole month. So let's move forward and look at some practical stuff. So now we have the OS nodes, and I talked about the nodes there. If I execute, you can see that right now I have two nodes, node 0 and node 64. And as I said, this is a laptop, so it's not really a kind of a multi-NUMA node system. 64 is for DAC and 0 is the default node that I have. And for each node, I will have a mapped memory node inside SQL Server. I can see some notifications on the chat. Yeah, okay.
We can do the questions afterwards. I'm collecting them.
Yes. Okay. Okay. Thanks, Daniel. Yeah, friends. So please hold on to your questions. The chat window gives me a notification, so I kind of get tempted to look at that. Okay. Anyway, I will carry on. Now, when you look at the memory nodes, friends, if you see here virtual address space, and now you get a very low-level information of how all these numbers are coming from. And really, given the time, I would love to talk about where all these numbers are coming from, but I just have like 25 more minutes to go through the demos. Now, let's look at important stuff. Memory clerks. So when I execute here, you can actually see all the different clerks here: general clerk, the buffer pool, query compile, query plan. And when you look at the names of these clerks, some of them are kind of quite self-explanatory as to what these clerks are doing. I would put it this way. So the components inside SQL Server that need memory, they kind of have their clerks. So you know what is the memory being consumed for. And when you want to see the total amount of memory that they are actually using, so or basically reserving, you can actually add up these, the pages KB, the virtual memory reserved, and the virtual memory committed, and you get the amount of memory. And then if you look at one of the columns here, you can see is memory clerk address. And more important than memory clerk address, I want to show you page allocated address. This is important. This is actual allocation in the physical memory page. And where does this come from? This comes from the memory objects. Now, memory objects are the most granular level of information. So apart from object address, you can see pages in bytes. Now that's kind of interesting because pages clerk were in kilobytes, and of course these are very hundreds of small objects. They are in bytes. So kind of add all of them up for a given clerk, you should see the amount matching theoretically. And you have all these different types of objects. They say what they are being used for, and you can join clerks and objects using this DMV called page allocator address, which you saw in clerk also. So let's do this simple test here now, just to show you. So if I look at my current memory consumption, and you can see now I'm adding pages KB, virtual AWE allocation. Now this AWE allocation right now beyond 2012 you don't need. It's just a query that I'm running because the value for that is anyway going to be 0. So if I execute that, you can see that buffer pool is currently consuming 90 MB. So kind of, let's do a bit of accounting here. So you had like 360 MB being used by the process. Buffer pool is using now 90 MB. And what's the bifurcation of this 90 MB of the buffer pool? So if you know, there is a DMV called sysdmos buffer descriptors. If you look at line number 42, the DMV is out there. And if I kind of execute this and try to get every page information in this DMV OS buffer descriptors, there's one record for every data page. So you have the file ID, the database ID, and the page ID. And if I sum up all of that, I can see that resource DB, the hidden database, is using 24 MB. But look at AdventureWorks 2014. That's only using 5 MB right now inside the buffer pool. And if I use AdventureWorks 2014 and I want to drill down as to which all tables are really hogging up this 5 MB, 5 MB is nothing, but just kind of for the purpose of the demo, you can see this is how the distribution of that 5 MB for AdventureWorks 2014 is inside the buffer pool. And let's do a quick test. If I open up this new window and I say select star from sales order detail, that's kind of one of the bigger tables compared to others, and I do an execute all there. Now what has happened, a few hundreds of pages have been loaded from disk into memory, so of course you will be needing more memory. And now the moment I execute this again, remember sales order detail was somewhere here with just less than an MB, and now if I execute this, you can see sales order detail comes up on top with about 9.7 MB of usage. And likewise, if I see the database wise distribution of my buffer pool, AdventureWorks 2014 should show 15 MB now, which was kind of 5 MB. So see the numbers are kind of lining up, 9 MB, 10 MB kind of things. And of course, there are a lot of system pages also that are already there in the memory. And if you see the buffer pool, which was 90 MB, if you execute, you can see it's gone to 101 MB. So you see how buffer pool, now buffer pool is also a clerk, and that's right there in front of you. I'm saying DemOS clerk, where type is equal to memory clerk buffer pool. So I'm kind of tracking memory usage inside SQL Server. And of course, what if I say dbcc drop clean buffers, and all of you know what this would do. This would actually clean the buffer pool, and not a good thing to do in your production environment. This is just for the purpose of this demo and test. And you can see now buffer pool is just back to 21, very bare minimum. And if you look at what the databases are consuming, and all numbers will be pretty, 0, everything, all good, right? Now, this according to me was one of the most basic things I could show about memory consumption inside SQL Server with the buffer pool. Let's go a little deeper and let's try to see something with clerks and objects now. So now let's say there is a clerk, and by showing you these demos, and I know I'm going fast because the need of the hour is to go fast. I am trying to show you a clerk called cache stored PHDR, and cache stored PHDR is for bound trees. And if I execute this, look at the amount of memory it's consuming. So 1120 plus 0 plus 0, which means I'm using kind of close to 11, 10 or 11 MB there. That's the KB size. So if I take up all the memory objects, and there is a type here, where is the pages in bytes, and let me scroll down a bit there. Memory object
I think it was there a little to the right.
Little to the right.
So on left.
Okay. I think it is type, right? So you can see the type here, cache stored PHDR. So I can let me see memory objects where I will want to show you all the memory objects that are for my clerk cache stored PHDR. Okay, so let's do this and we execute this. Okay, so I have to, that's fine. I think I'm going wrong there. What we need to do is, this is correct. I am actually joining. So as I said, we are joining the clerks and the allocators on clerks and the objects using this DMV called page allocator. And then I'm filtering on the cache stored PHDR. So if I take all of this, I will only get my memory objects for cache stored PHDR. And if I execute this, there you go. This is what I wanted to show you. So you have all these clerks, cache stored PHDR, and you can see all these objects that belong to the cache stored PHDR, which is the memory that is being consumed by this clerk, right? Allocated, which structured allocation is broken down into so many different objects. And this is their consumption page in bytes. So what if I actually sum all of this up, right? So I should get, trying to prove the concept here, I should get 11120. And if I sum up all the pages in bytes for memobj parse, I should get 11088. So something is missing. What is missing is, if I run this again and show it to you, memobj parse, there is one more object which is not of this type, which is the root object probably, which is memobj cache store PHDR, and the size for this is 32768 bytes. So if I add 32768 there And then if I try to execute this, should be 1120. Let me just give this a number again. Pages in bytes. 32768. Missed out on the number, but it should come on 1120 again. But anyway, we can, if I have some time, I will try this again at the end. So the whole idea is I was trying to see how the memory clerks get broken down into these memory objects. 2540, why did I was doing that? 1120. Okay. Let's do a quick restart to kind of play around with this once more. When demos, the numbers don't catch up, specifically in cases of memory, it's a little suspense. So let me give this, another try. So when I do this, first I would see how much I have in my cache stored PHDR. And okay, now it's pretty low, 2392. And let's take this together, 2392. Did I? Okay. And my number there is 491,491,5. Okay, no, this one cache stored 8192, cache stored object. So 8192 is what I will do. And let's add this up here because
yeah, one of the attendees says put 32768 outside the sum bracket.
Okay, outside the sum bracket. Okay, let's give this a try. So 2840. Was it 2840? Anyway, for the sake of time, I would let it go, but this should have been working. Oh yeah, actually, thanks to that attendee. He's actually right. This is what I was going wrong. 2600? Is that my number?
I can imagine the DMVs also fill up the buffer pool. So
yeah, no, it's fine. So we get the number. So we see the cache stored PHDR. Thanks to that attendee. Can I have his name, Daniel?
It's I can't pronounce it. There's two of them, Jim Higgins and Lesur.
Thanks, Jim. Thanks, guys. So yeah, thanks, guys. So if you can see the cache stored PHDR is now 2600, and this is what I was trying to sum up all of them by adding that one object which was of a different name, not memobj parse, and I added 8192 manually, and I get 2600. There you go. So basically, I was just trying to prove this concept of the three-layered architecture. You know, if you visualize that diagram again, that the lower level you have the objects and the clerks, and then the memory nodes, then they talk to the NUMA nodes, etc., and try to allocate memories via Win32 APIs. Now, let's look at a real example of memory troubleshooting. So I will close this and let's quickly get started. So what's my message? My message, of course, and the purpose of this webinar was to give you a brief overview of the memory architecture, show you some numbers floating around, and now we'll troubleshoot memory with an example. And for the purpose of this demo, I will go to my, I go to memory, and let's take a demo here. Daniel, by any chance, can we extend by 5-10 minutes, or how does that work?
We have a 15-minute break before the next speaker, so I'm sure five minutes is probably okay.
Okay, so when I look at, let's quickly do this. So there is a utility here called RML utilities, and then I'll get this quickly installed, and it's just as quick as this. And RML utilities has a tool called ostress, which will help me stress SQL Server using a file. So let's get started. First, I will open up my, let's see how much memory are we consuming right now. So right now we are consuming, let's say 328 MB. For the purpose of demo, I will set this memory, max memory, to 550. You should never try doing all this stuff in your environments. This is only for the purpose of this demo. So what am I trying to do? I am trying to create an out of memory condition, and then we will troubleshoot where things went wrong. So just to create that memory condition, because there's like 16 GB memory here, and I really don't want to hog up so much, I'm setting it to 550 MB. So let's execute that. And I got an error because sp configure show advanced option. Why is that an advanced option? Seriously. So let's do this again. Execute, and 550 MB is what we do. Okay. So max memory is being set to 550 MB. Boom, we go, and we'll keep this window on. And now here we know we are in 328 MB, and I've just put two queries here. So I'm looking at OS process memory, then I am looking at all the memory objects, and I'm ordering by total MB. So what I want to do is all high memory consuming objects will come on the top. Right now, if you look at the output, SOS node, which is the OS SQL OS scheduler node, is on top, and then CLR and all that stuff, and then the clerks, finally the clerks. So you can understand that I'm playing heavy with clerks and the memory objects, and then again order by pages KB to see high consuming clerks on top. And let's keep this running. This is the output that we will see, and I'll just make it a little full window for you to see. This is what our scene is. About 329 MB of usage. Some objects are there on top, but nothing much. And then you have the clerks, and buffer pool being the largest memory consumer is right on the top. Now we go back to this place, and we'll take these two queries, and I will put them in C program files, Microsoft Corporation, and there is RM utils, because I'm calling this exe that you see in front of you, which is ostress.exe, and I'll call this leaks.emd, and then go back there. So let's begin. This is the timing is very important here. So I double click this, it's running. Let's go back, execute. Friends, keep watching. The physical memory is going up, 380, 404 MB. Look at memory objects now. There is a memory object called cursor execution that's going up, which is taking a lot of memory. Look at the clerks. Cache store SQL CP is going up. SQL plans. It has bypassed even buffer pool. So SQL CP becomes the largest memory consumer now. At some point, we had set max to 550. I told you 550 max memory is a soft limit. So somewhere it may go a bit up, but then a point will come when you might get OOM condition, and everything is hung up here right now. So SQL is trying to execute this query, but probably there's not enough memory now. Let's see how it's going. And it is just stuck up right now. I am just hoping that all of you watched this, and of course this webinar is recorded, so you can pause and watch again. There you go. So this is insufficient system memory and resource pool default to run the query. We have just hit an OOM condition, and even if I go and look at the command prompt there and just kind of pause for a moment, you would probably see the same thing there. Insufficient system memory in resource pool. So we just hit an OOM condition. Now here is my question to all of you. When something like this happens, what do you do, right? Because there's absolutely nothing printed in the error log. You have, DMVs are volatile. They just don't carry any information. So what do you do? This is an error that gets thrown down to the application. And now if I execute this one again, you remember, and all of you I hope remember, that cursor execution and SQL CP. So cursor execution in the memory objects and SQL CP in the plan cache, they were right on the top. What do you see now? Strange. So cursor execution is gone. You don't see that as a memory object anymore, but physical memory still sits at close to 600 MB. And when you look at the clerk, the SQL CP clerk is kind of again sitting down there. The question here is, how do you really find out what went wrong? Why did you get that OOM condition? And unfortunately, at this point, if extended events are not running, if you have not set up any kind of baselining, or you don't have any monitoring tool, or you're not really capturing capturing any kind of information, then going back into the history and trying to find out what just happened 5 minutes back is very, very difficult. So the purpose of this demo was to tell you that extended events is a good way on how you can capture some information periodically, because when you have this kind of information, this kind of issue, this kind of troubleshooting scenario, you can go back and look into the history or the captured records by extended events and try to figure out that, okay, there was something to do with cursor execution maybe, because the clerks and the objects will give you that hint. We do this manually by actually setting up some jobs which will actually kind of take top 10 objects by their memory consumption and top 10 clerks by their memory consumption every 5 minutes or 10 minutes or something, and dump it into a baseline database. Whether how much data you want to capture, how frequently you want to capture, and how long you want to retain, well, all those questions can be answered based on what your scenario is. If a customer is frequently getting such terrible errors, I would probably do that a lot more frequently. And in a more quiescent environment, I might just do it more in a more relaxed way. But you just saw that clerks consume memory and then they release. So it's like the clerk algorithm. The code behaves differently with different clerks. Sometimes they consume and they release, and sometimes they hold on to the memory. So let me show you another quick example. So when I was looking at this one, right, the clerks, and if I execute, you can see we are now, schema manager is there on the top there. Let me just move this window a bit, and I'll just go and run another query for the sake of explanation. If I go to memory in my first demo, let's see. Okay, and if I execute this one, and now if I go and check this, you can see SQL reservations there on the top, and you can see the amount of memory it is consuming, close to 100 MB there, right? SQL reservation clerk. Where does this come from now? And you can see what's happening. SQL reservation is running, and let me stop this query now. I will stop this, go back, and then execute this again. SQL reservation is gone. So you can see how SQL reservation clerk comes up when you have a memory intensive query, which is probably trying to do some expensive sort or hash. The optimizer, actually SQL reservation clerk is kind of attached to the optimizer, and it tries to reserve the memory upfront for those expensive sort or hashing operations. So that's another type of clerk. In fact, in this example, I was trying to show you different clerks, and you know how much sometimes some clerks release memory back and the others just don't. So I was trying to show you the connections clerk that release memory back. But if you take an example of the lock clerk, the lock clerk actually will not release the memory back, because you know lock objects are very fine-grained objects, and in any database you would always need them. So they hold on to those objects. So that's how different clerks behave. So back to the presentation. So here is a quick summary. What did we do? We talked about NUMA. We talked about a few myths and misconceptions about SQL Server Memory. We briefly looked at the SQL Server Memory architecture. Then I showed you how memory usage and tracking works. I just created a memory pressure example, just a simple one. And actually what I was doing in that demo was I was opening up a lot of cursor objects and I was not closing them. And that ate up all the memory. So just trying to create a memory leak situation. And then I showed you how you can troubleshoot. The answer to troubleshooting SQL Server Memory is clerks and objects. And of course, nodes and you know the process memories, they can give you some information, the counters, but clerks and objects are key to finding out the root cause of the bottleneck. Friends, if you have liked this demo, I will request Daniel to kind of put this up, or if he allows me to put up these links there. So I just posted this picture. This frame is pretty popular, the SQL Server Memory diagram. I have put this up on LinkedIn as a kind of a notification for today's demo. So if you have liked today's session, please go and give some feedback on LinkedIn. So on that URL. Ready to take questions? Yeah. Ready to take questions.
So the first question is minimum memory impact in case of VM is same as physical server.
This is a question that comes in forum where someone is trying to say, can I set min and max to the same value, which is kind of equivalent to the physical server memory? No, that's not a good thing to do. So the answer to that is straight away no. You definitely want to put min slightly lesser than what max is. Yeah.
Next question is, not much documentation on the net, but some error like app domain parenthesis number unloaded. You can see it in the webinar chat. But some error in like app domain number unloaded / loaded in SQL Server error log. Can you elaborate?
No, so I know this has come from Anupinder. No, Anup, I don't know about this. There are a lot of these messages coming. Yeah, sorry, I've never gone into that.
Yeah, I'm still confused about what the references to large memory model mean. We're using Enterprise Edition. Is that referring to trace flag 834?
Yeah, so I will just quickly clarify large page memory model once again. So there are two things. Does your SQL Server support large memory model? There are three conditions to be met. You need to be Enterprise Edition. You should be running Enterprise Edition SKU. You should have more than 8 GB of physical RAM, 8 GB or more. And third condition is locked pages in memory should be turned on. So this means supporting, which means SQL Server memory algorithms and allocations can decide whether large page model should be used or not. And sometimes when the conditions are met, you would actually see 32 MB of large page allocation happening on per node basis. It actually doesn't mean that large memory model is being used, but actually those are just large page buffers. At this point, I won't go much deeper into that, but now comes usage. If you really want to force use of large memory model, you have to turn on the trace flag 834. If you turn this on, then you're forcing SQL Server to run in large memory model. And what's going to happen? You put that trace flag, restart SQL Server. SQL Server will consume all the memory from Windows up to the max, whatever you have set. And then SQL Server will start allocating memory in large chunks using large pages. So those allocations could be from 2 MB to 16 MB, which are the Windows large page sizes on a 64-bit system.
And then finally, there was a question if you can share the scripts, and you think you did, yeah.
Of course. So just friends, if you can send me an email on amit.bansal@sqlmaestros.com, or I'll put it this way, connect with ab@sqlmaestros.com. I will share the scripts with you.
Those were the questions, I think. Let's see. So thank you so much for presenting.
Right. Great. Thank you, Daniel. Thank you, Michelle, Blythe, and all of you, the new team of Groupby. Thanks, Brent, for conceptualizing Groupby. So it was great to present today. Thank you very much. And yeah, I want to thank the SQL community, all the product team members and the MVPs and the worldwide community, because it's with a lot of interactions, attending MVP summits and talking to product team members that sometimes you gain so much knowledge and expertise. So yeah, all credits and kudos to all of them, really.